Welcome to the review session on applied thermodynamics. So what we will do today is go over the topics which were discussed in the past 12 weeks. We'll try to cover in short what was taught, what was covered in this course, applied thermodynamics course, and just the concepts which I'll be discussing. So starting with the first week was basically a recap on thermodynamics, application. So your entropy and exergy, how to apply an exergy balance, and how to do problems on those. So with that, the next where we were started with cycles. So with that, we started. The first one was the Carnot cycle. So we need a basis to compare our cycle and to see how much efficient can we make the cycle, or how much more can we improve it. So we need a baseline, or we need a goal. So that's where to reach. So we are designing cycles, and we are constantly trying to improve these cycles. So so we need to have an idea how much can be improved, or which component can be improved. So for this we need a ideal cycle on which this comparison can be made, because if you are testing it at different conditions and so on, you cannot compare these two together. But this ideal cycle, when it's running in the similar case scenario, it gives you an idea of how the actual cycle is performing, and it also makes it easier for comparison. So with that, one of the ideal cycle which we use for comparison is the Carnot cycle. So Carnot cycle consists of 4 processes. We see it was an isothermal compression, and then you have isentropic compression, then you have isothermal heat addition or isothermal expansion, and then isentropic expansion. So this 4 processes, so 2 isothermal and 2 isentropic processes. So this also we discussed how Carnot cycle, how it can be, what the difficulties in using it practically. So you see isentropic processes are very fast processes. So the normal compressor or mini turbines, these are running at very high speeds, and the time it has for heat transfer to occur is very small. Hello? Hello? So this isentropic process are very fast, so it will not have enough time for heat transfer to happen. So that's why I assume it to be an isothermal process. Excuse. Hello? 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 Huh? Yeah. Hello? Yes. Fine. Can I call you back in after an hour or two? I'm in a meeting. So it's an isentropic process, and then isothermal process. If you see, it has both heat addition as well as work interaction. So this both has to take place simultaneously. So this is very difficult. So for that to happen, this process has to be very slow. So you, in ideal assumption of quasi-static process which we assume. So that has to happen. You go with incremental amount, small incremental amount, and let it come back to the same temperature. So these are all practical difficulties, and we also uh, uh, which it will become very bulky, higher, bigger size compressors, and so on, which we discussed during Carnot cycle. And then uh, to uh, to have an actual cycle, we said this isothermal can be obtained when we use a pure fluid and when we are putting it inside a two-phase dome. So that's what we did, and then that isobaric process is equivalent to an isothermal process in this case, because pure fluid when there is a phase change, it happens at a constant temperature. Then we said your isentropic process which is happening as a 1 to 4 or 2 to 3, so this is happening in a two-phase region. So handling this two-phase region in compression or expansion process, it's not good. So you may have difficulties there because your turbine blades may roll, and when compression, the liquid being incompressible, it may damage your compressor. So on other kinds of problems which will come. So we limited how much liquid it can be handled in evaporator. So we saw the numericals also, fixing your evaporator exit at some dryness fraction, and we saw how to evaluate a system or design a system. And also your compressor inlet, we are assuming it to be in case of vapor compression. So here we will be using a pump. So the advantage of this one is being liquid, the specific volume is low, so the work done to compress the pump the fluid will be low compared to a compressor. So your total work done is smaller in case of a pump, because your specific volume of liquid is very small. Then you send it to an and then we are pushing this two isentropic processes outside the two-phase region. So basically this is how the cycle will look, and this is called as an Rankine cycle. So this Rankine cycle also contains of four processes. So one is an isentropic compression, where you are pumping the fluid from 1 to 2s. So but ideally the isentropic doesn't have follow constant entropy line. There will always be friction and so on, so it's not reversible. So you have some entropy which is generated. So you will have 1 to 2, so that is the actual process. And then you are sending it to a boiler where you are adding heat and you are generating steam. So 2 to 3 is your heat addition. So this happens at constant pressure, so it's an isobaric process. Then after 3 you are expanding it in the turbine and then cooling it in the condenser. So this is a Rankine cycle. So and the mass balance and energy balance is all listed for each of the components here. So this is your Rankine cycle, and your efficiency of Rankine cycle is nothing but your work which is generated, net work. So work output minus pump work, but generally we neglect the pump work, so which will be very small, so negligible compared to the work we are getting in the turbine. And there's also the back work ratio. As I say, it's very small. It's how much work you are utilizing with what you are generating. So that is very small. So the efficiency is your net work divided by the heat which you are added, Q in. So that will give you the efficiency of the cycle. And the rest of it is, or you can get it from the enthalpies at each of the points. So that's how a Rankine cycle works. So the first one, the thermal power plants generate electricity by using fuels. So they burn basically coal, oil and natural gas, and they use a Rankine cycle using steam as the working fluid. So the vapor, so that's what this Carnot cycle, when you are operating at in the vapor phase, ideally can work as Carnot cycle, but there are practical difficulties. So efficiency of the Rankine cycle is given by efficiency work by Qs, the heat supply. So work is H1 minus H2 is the turbine work, specific turbine work, minus the pump work. This is all in specific quantities. So you have to multiply by mass if you want. Then there's a term called specific steam consumption. The specific steam consumption is defined as the mass of flow of steam required to develop unit power output. So this we require in hour, kilowatt kg per hour. So 3600 to convert into hour, divide by work. So basically your specific fuel consumption is for getting 1 kilowatt of power, how much mass has to be supplied. So 1 by W. So here converting it to from seconds to hour, you are multiplying by 3600. So specific steam flow rate is now in terms of second. So kg per kilowatt is 1 by W. So the work ratio is defined as the net work by turbine work, and that is the work ratio. So for actual Rankine cycle, work output is given by your change in enthalpy across the turbine. So isentropic efficiency is actual work by isentropic work for an expansion process, and so the other way around, this is isentropic work by actual for the compression process. Then the efficiency of a reheat Rankine cycle is given by before going there, we will see the variations in Rankine cycle. So how to improve efficiency of Rankine cycle. So either we can push the evaporating pressure down, so this will give you an increased work output, but this will also have an increased pump work, but basically that pump work is small, but this is limited by my pressure which we can handle in the evaporator, and if it's lower, it may go into vacuum and so on. So the other problems which has to be taken care. So reducing your evaporator pressure can result in an increase in work output, but there is a slight increase in your pump work. So heat input also is increased. So the net increase the efficiency, it has to be taken. Will be an increase, but it will not be but a huge margin. So the lower limit on the condenser pressure cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. So also it's limited by what kind of fluid you are using to cool, at what temperature you are trying to cool. So if your evaporator pressure is lower than your water coming in at suppose 20, and this temperature is cannot go below 20. You need at least some temperature for heat transfer to take place. So that's the limitation here. Then higher moisture content at exit. So this will also give you a larger moisture content at the exit of the turbine. And then was your increasing your temperature to the inlet of the turbine. So that superheating and higher degree of superheat. So this effectively increases your mean effective temperature. So that will also give you an increase in efficiency. So this shaded portion is your increase in work which you are getting, but you have to also give some additional heat. And the other is your increasing your condenser pressure. So but limiting your temperature, your there is a decrease in work, and there is also increase in work. So this may or may not increase your efficiency. So next is we saw each of the components of the turbine. So the turbines can be of two types. One is an impulse turbine and another is a reaction turbine. So impulse turbine, basically it's driven by the pressure, the impulse which is coming and hitting the blades. So the pressure drop all happens in the nozzle, and there is no pressure drop across in the blades. But in reaction turbine, you have both the pressure drop in the nozzle as well as in the when it's moving in the blades. So this is driven by the reaction force. So that's the major difference between the impulse turbine and reaction turbine. So the impulse effect of the steam jet is what drives the impulse turbine, and impulse effect plus the reaction force is what is driving the reaction turbine. So this is how the velocity and pressure diagram looks. So initially the steam is at higher pressure. Across the nozzle the pressure decreases, which gives you a rise in velocity, and then when after heating and moving the plate, so the velocity drops. And similarly in a reaction turbine, so that's the initial drop in the nozzle, and it is rising the velocity, and then when the steam is exiting the turbine blades, because of it's driving the reaction force, the pressure again reduces in the blades. So in this case, in turbines impulse jet, there is a high jet velocity and blade velocity, but in this reaction turbine you have low jet velocity and low blade velocity. So the degree of reaction is defined in a reaction turbine. So it's the enthalpy drop across the moving blade, and divided by the enthalpy of the total enthalpy drop in fixed blade and the moving blade. So this we saw area of blade channel is constant, but it's of converging type in terms of reaction turbine. So blades here, if it's a profile type, and it's an airfoil type in a reaction turbine. So admission of steam, so it's not all round. So here it's admitted all around. So power, there's no much power generated in case of impulse turbine, but much more power is generated in terms of reaction turbine. So your size is also smaller in case of reaction turbine. So in terms of impulse turbine, but so it requires less space for same power and requires more space for same power. Your efficiency is low in case of impulse turbine, and it's high in reaction turbine. Similarly, we saw the nozzles. So for nozzles, we also defined the sonic velocity, or the velocity of sound in the fluid. So which is given by C equal to root of dP by d rho. So the Mach number is nothing but your velocity divided by the sonic velocity. If it's greater than 1, you are having supersonic, and if it's less than 1, you are in subsonic flow. So the flow through the nozzle is given by dA by A is m square minus 1 into dou V by V. So it's nothing but your mass balance. So your flow rate will be same. So with that you will get this expression. So this says that when you are in subsonic flow, you will have minus dV by V term. So m will be less than 1. So in that case, the right hand side will be negative. So that says that your dA should be negative. So it should have a converging section in subsonic flow for there should be an increase in velocity, and similarly it will act as a nozzle, and if your Mach number is greater than 1, then it will act as a diffuser. So if you have some supersonic flow at inlet, so then converging passage will act as a diffuser, and diverging passage will act as a nozzle. So this all is given by this expression here. So for you need a Mach number greater than 1, you need to have a converging diverging nozzle. Then we saw boilers. So boilers you have of two types. So your fire tube, and where you have hot gases passing through the tubes, and then the normal conventional boiler where water is passed and both are arrangement of a shell and tube. So here hot flue gas passes through the tube and it heats the water surrounding the tubes. So this takes more time for the plant to start, because the heat steam generation rate is small, so the rate of steam generation is lower, and it also generates low pressure streams. So this is generally used in cases where you have heating in chemical process, and also where process steam is available, is required. Here generally is the hot flue gas goes outside the tubes and water is passed inside the tubes. Here the disadvantages in the above case is the advantages here. So you have high steam generation and you can generate high pressure streams. So this is and it takes very less time. So this is suitable for high capacity power generation. So this is what you can see. Fire tube boilers, your operating pressure is low, limited to 16 bar, and here it's close to 100 bar. And the bursting risk of bursting is lower in case of fire tube boilers, but the risk is more in a water tube boiler. And fire tube boilers requires bigger sizes, and compared to a water tube boiler. The construction is also difficult, and in case of fire tube boiler, but it's easier in case of water tube boiler. So next is we saw this comparison how an engine power producing and power absorption device in a compressor and so on, how it is cooled, what type of cooling. So it can be spark ignition, combustion ignition, it can be rotary type in a Wankel engine, and it's a rotary type. So and then spark ignition can be either petrol or gas engine. It can be air cooled or water cooled, or the type of operation being 2-stroke or 4-stroke. So this all we saw. Or it's an internal combustion engine. Similarly, you can have an external combustion engine. So this is a brief chart on that. So advantage of reciprocating internal combustion engine over external combustion engine is efficiency is high. You have greater mechanical simplicity. So and have weight to power ratio is low. You have initial cost which is less. So it's easy to start at cold condition, and it is very compact. And it requires very small space. But if you see external combustion engines, the starting shock is generally very high. So because of external combustion of fuel, cheaper fuels can be used, even solid fuels can be used advantageously. There is no flexibility in this case of external combustion. So these are self-starting. You need some additional device in case of an internal combustion engine. So this is how an air-cooled internal combustion engine works. So this we saw what are the components in an internal combustion engine: the cylinder, the piston, and the outside are the cooling fins, the inlet valves and outlet valves. The top is called the crown of the piston, and you have crankcase, and one is connected to that is a crankshaft, and the piston pin, it's called wrist pin, and the connecting rod between the crankcase and crankshaft and the piston. So this all we saw each in case how the construction of an internal combustion engine is. Then we saw compression ratio, and then this defined what is an square engine. So when the bore stroke length is same, it's called as an square engine, and if it's greater, it's called diameter is greater, it's called over square, and if it's less, it's called under square. And your indicated thermal efficiency is called indicated power by heat supply, and similarly brake thermal efficiency is brake power divided by Q, and this difference between indicated power and brake power is a friction power, so that is lost due to friction. Your combustion efficiency is the heat which is supplied divided by the calorific value of the fuel, and the mechanical efficiency is your brake efficiency, brake power divided by indicated power, or brake mean effective pressure divided by indicated mean effective pressure, or your brake thermal efficiency divided by indicated thermal efficiency. and your volumetric efficiency is the mass of air which is going in divided by the mass during this occupied by the swept volume, your rho into the swept volume or displacement volume. And then we saw how a 4-stroke engine works. So in the suction stroke, the suction valve opens and you have air and fuel which is coming in, and then that is getting compressed, and there is a spark ignition which is made, and this fuel combusts and it creates a high pressure and it will move the piston down. That is called the power stroke, and then it will come back again, which is called where after coming in, the exhaust valve is open and the gases leaves. So this is how a 4-stroke engine works. And similarly in 2-stroke engine, in this 4 strokes, 4 processes are combined into 2, simultaneous 2 will happen. So while compressing, there spark plug, so it will the fuel will burn and it will push the piston down. So when it pushes the piston down, so it will compress the fluid which is there inside, and when it comes down, the exhaust valve will open and the fuel air will go out, and when it goes down again at some more distance, the inlet valve will the inlet air and fuel mixture which is there inside the crankcase will flow through the inlet port to the cylinder, and then again the piston will start moving up and compressing it. By the time the inlet valve opens and new fluid comes and occupies the crankcase, and this process is repeated. So this is how 2-stroke engine works. So here that 4 processor are combined together, and this happen in 2 strokes. So there it takes 4 strokes for a processor to complete, a cycle to complete, or your 2 rotation of a crankshaft. But in this case, a single rotation finishes the whole cycle. So if you compare the 4 strokes and 2 strokes, so the cycle is completed in 4 strokes. Here it takes 2 strokes, or in 2 revolution of crankshaft in case of 4 stroke, and 1 revolution in 2 stroke. So the flywheel is required is higher in case of 4 stroke, because you need that much energy to finish the cycle. So you are having only 1 power stroke, but 3 process you are getting the energy to drive it from the flywheel. So that is lighter in case of 2 stroke. So power produced, because there is only 1 power stroke for 2 revolution, the power produced is little less compared to 2 stroke. So initial cost, because of the heavy weight and valve mechanism, higher is the initial cost, but in 2 stroke this is cheaper, but volumetric efficiency wise this is 4 stroke valve is better compared to a 2 stroke engine, and thermal efficiency is also higher in case of 4 stroke engine compared to a 2 stroke engine. And this internal combustion engine can operate in 3 cycles, first being the Otto cycle, and then your diesel cycle, and a dual cycle. So Otto cycle, you have reversible, first one is reversible adiabatic compression 1 to 2, and then you have a constant volume heat addition, and then 3 to 4 is reversible adiabatic expansion, and 4 to 1 is a constant volume rejection, or that's exhaust basically. So this is the cycle. So the efficiency for Otto cycle is given as 1 minus 1 by pressure ratio raised to power gamma minus 1. So your Otto cycle has 2 constant volume presses. In diesel cycle, the heat addition is changed to a constant pressure process. So 1 to 2, the rest will be same. So 1 to 2 reversible adiabatic compression, and then 2 to 3 heat addition, constant pressure heat addition, 3 to 4 again isentropic expansion, and 4 to 1 is a constant volume heat rejection. And the same is shown in a TS diagram. So for this, the efficiency is given as this. So same expression as your Otto cycle. Your additional term with 1 by RP raised to gamma minus 1, being beta raised to power k minus gamma by minus 1 divided by gamma to beta minus 1. So this is your volume V2 by V3. And similarly, your air standard dual cycle. So here you have heating addition happening in two process. So this combination of both the diesel and Otto cycle. So is having first constant volume and then it happens at constant pressure. So this is how a dual cycle works, and the expression for efficiency is given like this. Then you have a comparison of Otto, diesel and dual cycle. So when you have same compression ratio and heat rejection, so this is how the process looks like. So this has same compression ratio, so 1 to 2, your compression ratio is same. Then when you are limiting same, your heat rejection is same. So this is how the process looks. So 1, 2, 3C is your diesel cycle, then X3B is your dual, and 3A 4 1 is your Otto. So Otto has more work, so your efficiency of Otto cycle is more, then dual, and then the diesel cycle. But if you are having same maximum pressure and temperature and same heat, different compression ratio and same heat rejection, then this is how the process looks. So in this case your diesel cycle will have more efficiency, then dual, and then last will have a Otto. So Carnot cycle is represented as standard of perfection in engine. So that efficiency is given as 1 minus T1 by T3. So heat rejection by heat addition. So the Carnot cycle has a low mean effective pressure because of its very low work out. So basically the Carnot cycle, ideal cycle, your work output will be very less, even though efficiency is high. So Stirling cycle efficiency is given by so the efficiency of Otto cycle is given by 1 minus 1 by Rp raised to the power gamma minus 1, and work output is given as P1 V1 by gamma minus 1 into Rp minus 1 into Re raised to the gamma minus 1 minus 1. Rp is the pressure ratio and R is the compression ratio. So mean effective pressure of Otto cycle is same, the work done divided by your volume. So the ideal diesel cycle consists of 2 isentropes and 1 constant pressure and 1 constant volume process. And similarly, this is how the efficiency and mean effective pressure looks. And similarly for dual cycle. So for same compression ratio and heat addition, your or same pressure compression ratio, if you are having same compression ratio, your Otto cycle will have highest efficiency and the least will be diesel. And if you have same peak pressure or the maximum pressure, in that case diesel will have higher efficiency. So here there is some mistake. So diesel will have higher efficiency when you have same maximum pressure. And similarly, just like Otto, your efficiency of Brayton cycle is also same. So 1 minus 1 by R raised to the power gamma minus 1, where R is the pressure ratio. So this is how Brayton cycle looks. It's just similar to your Rankine cycle, but instead of operating in a two-phase region, it's operated in a vapor region or superheated region. So this A, B, C, D is your Brayton cycle. So similar to that, it was here 1, 2, 3, 4. This is your Rankine cycle. So when you are moving it out of the two-phase region, it becomes a Brayton cycle. The fourth process is same as your Rankine cycle. So isentropic compression and then isobaric heat addition, then isentropic expansion and then isobaric heat rejection. So that is your Brayton cycle. So your Brayton cycle with respect to pressure ratio, when you plot, it has an optimum pressure ratio where you will have maximum work, and that optimum pressure ratio is given by Tmax by Tmin raised to the power gamma by 2 gamma minus 1. So that gives you the pressure ratio where you have maximum work, and when your pressure ratio is 1, so there's basically you're not having any work output, so there's no cycle. And when you are having maximum pressure ratio, again your work your compressor or will have the volumetric efficiency becomes 0, and there will be no work which is generated. So in that case, both case work will become 0, and there's goes through maxima, so that maxima is given by this RP opt, and the work corresponding to this maximum work corresponding to this optimum pressure ratio is again m dot Cp into root of T max minus root T mean the whole square. So a variation of this is using an intercooler or a multi-stage intercooler and reheater. So even though this may not give you an increased efficiency, but it boosts the efficiency is increased a great extent when a regenerator is being used. So with that, next is we saw was vapor compression cycles. So vapor compression cycle again is similar to a Rankine cycle, but you are running it in reverse, and instead of your expansion, isentropic expansion, you use a isenthalpic expansion. So it's simpler because you cannot handle two phase. So you are using an orifice or valve or a capillary tube in this case, and so that gives you a isenthalpic process. So then your process comes to be isentropic compression, then isobaric heat addition, heat rejection, and then isenthalpic process, and then isobaric heat addition. So this is how the cycle for a VCRS cycle looks. So in this case, you have a mechanical compressor which is doing the work. If you are replacing that with a thermal compressor, so this is how a thermal compressor looks. So in this case, you have an absorber, pump, generator, and a valve. So the fluid which is coming out of evaporator, so that gets absorbed in absorbent, which is pumped in the pump to a generator. So if you have any excess heat in a plant or something which you can utilize, which you are dumping, even though it has some energy which can be utilized, so you can run this thermal compressor, you can use that heat, so which will generate the vapors. That vapor is sent to the condenser, and the absorbent is brought back via valve to the absorber. So this is how a vapor absorption refrigerant system works. So the other part will remain same. So just the compressor is replaced with the thermal compressor. So the examples of fluids which are used is an ammonia water refrigerant or lithium bromide and water refrigerant. So in ammonia is a refrigerant and water is your absorbent, and lithium bromide water is your refrigerant and lithium. So this is how absorbed in an evaporator for the cooling capacity divided by the work input. So relative COP is or second law of efficiency is actual COP by theoretical COP. So theoretically is to vary the Carnot COP. So the term is the ton of refrigeration. So ton of refrigeration is 14,000 kilojoule per hour. So what that basically means is 1 ton of refrigeration is defined as refrigerating effect produced by the melting of 1 ton of ice at 0 degree Celsius in 24 hours. So since latent heat of fusion is 336 for ice, so 336 into 1000 for 1000 kg of ice, so it becomes 1000 kilojoule. 1000 into 336 kilojoule for 24 hours. So divide by 24, that gives you 14,000 kilojoule per hour. So this comes out to be 3.5196 or 3.5 kilojoule per second or kilowatts. or 210 kilowatt kg per minute. So the ideal COP for refrigerators cold temperature source divided by T1 minus T2. So the factors affecting the performance of are your suction pressure, discharge pressure, the amount of superheat or subcooling, and your suction temperature and condenser temperature. So next is volumetric efficiency. So volumetric efficiency is defined as the ratio of actual volume of gas drawn into the compressor on each stroke to the piston displacement. So the ratio can be given as here the volumetric efficiency 1 plus C minus C into Rp raised to power 1 by gamma or 1 by N. So where C is the clearance volume, V3 by V1 minus V3 is the displacement volume. So the refrigerant in the vapor absorption system. So with that, next is your psychrometry. We saw psychrometric process and how psychrometric chart looks. So what are the quantities defined there? So you have the moisture content is given as a specific humidity, and then you have relative humidity, how much you are varying from the saturation condition, and then you have this saturation line where the air is totally saturated, cannot take much more any more air, and at this point the dew point can the temperature when it's saturation corresponding to that temperature it can form the first dew. So that is the dew point temperature here. And also we saw the wet bulb temperature, and dry bulb temperature is the air temperature. Wet bulb temperature is when you have dipped in a wick and the air when you are rotating the air it comes in equilibrium. There is a mass transfer and energy transfer, and it comes into equilibrium. So when the thermometer shows that temperature, it's called the wet bulb temperature. And you have again this wet bulb constant wet bulb line. So this will be parallel to again the enthalpy lines. Then you have this relative humidity lines which we shown in a cycle. You have specific volume lines. So you have this is an oblique chart. So your dry bulb temperature is given at the bottom, and the vertical axis gives you specific humidity, and you will have an scale for enthalpies at the top of the curved portion, and then this is how the process is happening is represented. So 0 to A is your sensible heating, and 0 to B is a sensible cooling, where there is no change in mass of water, so you are just heating it. And then 0 to C and O to D is your humidifying and dehumidifying. So in humidifying you are adding water, but your temperature is not changing. So in that case it's humidifying, and then if you are removing water it's dehumidifying, and then it's the combination of process heating and humidifying. So 0 to E, and then cooling and humidifying is 0 to G. So similarly you can have cooling and dehumidification and heating and dehumidification. So you see psychrometric is general term used to describe physical and thermodynamic properties of gas vapor mixture. So other names is involve psychrometry and psychometrics. So the dry air term is air which is devoid of moisture. So it's free from contents of water. So when the moisture content is maximum, the air is known as saturated air. And then dry bulb temperature is the temperature of the moist air registered by standard thermometer or any other temperature measuring instrument. So wet bulb temperature is the temperature registered at a thermometer when a thermometer bulb is covered by a wetted wick and is exposed to a current of rapidly moving air. So that is WBT. The saturated vapor pressure, it is saturated partial pressure of water vapor at the corresponding dry bulb temperature. Then adiabatic saturation temperature. This temperature at which the water or ice can saturate air by adiabatic evaporation into it. It is numerically equivalent to measured thermodynamic wet bulb temperature. Then wet bulb depression is your difference between the dry bulb temperature and wet bulb temperature, and then dew point depression is the dew point temperature is if unsaturated moist air is cooled to at constant pressure, then the temperature at which the moisture in the air begins to condense is known as dew point temperature. So that basically your saturation temperature corresponding to the vapor pressure of the air. So dew point temperature depression, it is the difference between the dry bulb and dew point temperature. And then degree of saturation is the degree of saturation ratio of humidity ratio to the humidity ratio at saturated mixture. So omega by omega s is your degree of saturation, and absolute humidity is the measure of water vapor in the air. So mass of water divided by mass of dry air, so that gives you the absolute humidity. The specific humidity, absolute humidity in terms of meter cube. So relative humidity is again ratio of partial pressure of water vapor in the mixture to the saturated partial pressure of the dry bulb temperature. So PV by PV saturation. So that is your relative humidity. And then we saw yesterday numericals on your compressors. So basically the volumetric efficiency and the intercooling and reheating, intercooling process in a compressor, and how to calculate the dimensions and so on. With that, it finishes the applied thermodynamics course review. So we have covered all, glance through the concepts which were taught in applied thermodynamics. So with that, I'll end the session today, and all the best for your exams on applied thermodynamics, and thank you.